We've looked at how several atoms make up a molecule. But how do they know how many of each atom makes up a molecule? Well, it's primarily based on two concepts we looked at earlier. First, remember it was Joseph Proust who proved that substances combined in definitely predictable proportions every time. No matter how much water you have, it will always be composed of 2 hydrogen atoms to 1 oxygen atom in a weight ratio of 1 to 8. It didn't matter if you had 1 ounce of it or a ton of it. They combine in the same amounts every time. Very predictable. It is the law of definite proportions. Second, remember Lavoisier's law of the conservation of matter? Nothing is created or destroyed in a chemical reaction. The total number and types of atoms is exactly the same before the reaction as after the reaction. They chemically combine simply to form different substances. So, based on these 2 laws, that things combine in definite proportions, and that you can count on all the matter still being there and not just disappearing, they eventually developed a scale that actually weighs atoms. Really? Yes, but it's quite different than even this sensitive 200-gram balance. Very different. They call it a mass spectrometer, which literally means visual weight meter. Mass, weight. Spectra, visual, and meter. Mass spectrometer. It's a scale for atoms. This is the outside of a mass spectrometer. And inside, this is basically how it works. A sample of material is heated and vaporized. Then the vapor is injected into the machine. A high-voltage coil knocks electrons off the atoms, turning them into ions. And ions, as you know, are atoms with an electrical charge. Now they can be experimented on with magnets. Magnets are used to accelerate the particles, which are deflected around a curve by another magnet, so they hit a detector down here. The lighter elements deflect more than the heavier ones, of course, meaning that every element hits the detector in a very specific place because of its specific weight or mass. The detector keeps track of all the hits and prints a graph of exactly how much of each element or substance was in the sample. Now they can accurately write formulas since they know how much of each element is in any given sample. When scientists want to write their experiments down on paper, their formula must reflect what happens in the real world. It must reflect definite proportions and the conservation of matter. The formula at the beginning must match or balance with the formula at the end. It makes the experiments very systematic, very repeatable, and very accurate. Antoine Lavoisier and Sir Robert Boyle would approve. Sort of like these balance scales. If you start with 20 grams of matter over here, it must balance with 20 grams of matter over here. This business of measuring and balancing elements is called stoichiometry, named by the chemist Jeremias Richter, and not the same Richter as Charles Richter of the Richter earthquake scale, who lived about 200 years later. So, stoichiometry, a 13-letter word that literally means element measuring, the art of measuring the elements. Stoic for short. Really, balancing chemical equations is not too different than a cookbook. What's over here in the recipe ends up on the plate. Essentially the same thing, just in a different form. And some recipes or formulas are easier than others. For example, here is a simple formula for a milkshake. Notice that the formula we started with in the cookbook is the same as you now have in the blender. The milkshake equation balances. And some formulas are more complex, just like some recipes are more complex. Just look at this recipe for chocolate chip cookies. By experimenting in the kitchen, cooks find formulas that make stuff. And by experimenting in the laboratories, scientists find formulas that make stuff. Heating, separating, measuring, analyzing just how much of every element makes up a molecule. They write their formulas down. And the formula they start off with on paper or in the lab needs to equal what they end up with on paper or in the laboratory. In this way, industries know just exactly how much of each element is needed to make a new substance and how they work. And here's some examples. Scientists know through lots of experiments that hydrogen plus chlorine equals hydrochloric acid. But how much of each? This is a simplified way chemists balance their formulas. 1. Hydrogen plus chlorine equals hydrochloric acid, H2 plus Cl2 equals HCl. Hydrogen and chlorine almost never show up by themselves, but almost always show up in pairs. Technically, they call them diatomic molecules, 2 atoms in the molecule. That's what the little 2 means. Here's 2 of each atom. There are 7 diatomic molecules, and they form a letter 7 on the periodic table. They are nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, plus hydrogen. Second, they isolate each molecule on paper. I'll put them in a little box. 3. Take an inventory of the atoms. 2 hydrogens and 2 chlorines equals hydrogen and chlorine. 4. And then write numbers in front of the boxes until the inventory is the same on each side. H2 plus Cl2 equals 2 HCl. Done. In this chemical reaction, 2 hydrogen atoms are bonded and 2 chlorine atoms are bonded. The reaction is indicated by the equal sign. The end product is the same number of atoms but rearranged. Balancing the equation shows the chemist that they have the right numbers of atoms on each side. Now obviously, in higher levels of chemistry, there are greater complexities to balancing formulas, but the foundations are still the same. Chemists balance formulas by counting the number of atoms, then changing the numbers in front of the formulas until it balances. If there are 6 hydrogen atoms on the left side of the formula, there need to be 6 hydrogen atoms on the right side of the formula. If there are 4 oxygen atoms on the left side of the formula, there need to be 4 oxygen atoms on the right side of the formula. Here's some more examples. These magnesium fire-starting tools are sold in grocery and camping stores. Shave a bit of the magnesium off, and there's a flint included to spark the fairly reactive metal off. Scientists know that when you light magnesium on fire, it combines with the air, burns hot, and ultimately forms magnesium oxide. That formula is magnesium plus oxygen makes magnesium oxide, which they found through lots of trial and error and experiments. Mg plus O2 equals MgO. But how do chemists balance this formula so it represents what really happened? How much magnesium? How much oxygen? 1. They write the formula. 2. Draw boxes around each molecule or compound in the formula and never change anything inside the boxes. Changing the subscripts changes the whole molecule or compound into something else. Chemists don't want this to happen. The compound is a unit, so that information never changes. So we will draw boxes to make sure that we leave the information inside alone. 3. Take an inventory of the atoms. This is kind of the fun part. You count all of the atoms on the left side and then the right side of the equation. You can also make a grid so you can list your inventory. 4. Then write numbers in front of the boxes until the inventory is the same on each side. Two magnesium atoms plus 2 oxygen atoms burns, forming 2 units of magnesium oxide. Here's another example, the famous table salt formula, sodium chloride. Burn sodium with chlorine and you get sodium chloride, table salt. But how much of each? Well, here's the basic formula. Na plus Cl2 equals NaCl. Now we need to balance it so that the same number of atoms appear on each side, obeying the law of conservation of matter. Draw boxes around each compound in the formula. Make an inventory of the atoms and a grid so you can list the inventory. Then write numbers in front of the boxes until the inventory is the same on each side. It balances. When sodium and chlorine combine, they combine in the formula of 2 atoms of sodium, 1 molecule of chlorine, and they form 2 ionic compound units of sodium chloride. Chemists call this number the subscript. These are the various elements, and the numbers they change outside the box are called the coefficient. It means to work with. And this is the number you work with to balance chemical formulas. And often they will replace the equal sign with this yields sign. But the equal sign gets the point across for us. But how do they get from a formula on paper to actually weighing something on the scales? They use the periodic table, of course. Let's take our salt example again, sodium chloride. After balancing a formula, they take an inventory of their atoms. 2Na plus Cl2 equals 2NaCl. Going to the periodic table, they see that each sodium atom weighs 23.0 and chlorine atoms weigh in at 35.5. They simply add it all up. 2 sodium atoms weigh 46 units. 2 chlorine atoms weigh 71 atomic units. So now they know that 46 units of sodium plus 71 units of chlorine yields 117 units of sodium chloride. You can even look at it as a percentage if you'd like. 46 is about 40% of the total weight, and 71 is about 60% of the total weight. With the knowledge of this ratio alone, a chemist can then weigh out any amount of the formula he wants, whether it be in grams or pounds or ounces or molecules or tons or whatever. That basically is how they do stoichiometry, how they measure the elements. Taking a formula on paper and turning it into real-world materials that makes everything from rocket fuel to silly putty to magnesium fire starters. By the way, it was inevitable that scientists would eventually ask, look, we're always talking about atoms, but exactly how many atoms are we talking about? I mean, exactly how many atoms are in this spool of pure copper wire? Well, first and foremost, it is important to remember that originally all of the elements were weighed against hydrogen, which was given the number 1, which we've seen. Gold is 197 because 1 gold atom is equal in weight to 197 of those light hydrogen atoms. And copper's atomic weight is 63 because it takes 63 hydrogen atoms to equal the weight of one heavy copper atom. Actually, copper's atomic weight is 63.5, but there is no such thing as half an atom or half a proton. 63.5 is the average weight of all the copper isotopes plus their abundance in nature. That's why there are fractions on atomic mass numbers. So, if a million hydrogen atoms weighs 1 pound, then a million copper atoms will weigh 63 times what the million hydrogen atoms weighed, and a million gold atoms would weigh 197 times what a million hydrogen atoms weighed. Because one heavy gold atom weighs 197 times what one very light hydrogen atom weighs. Atoms are all weighed relative to the weight of one atom of hydrogen, the lightest element. Since hydrogen is the standard, they wanted a count. They wanted to know exactly how many atoms were in 1 gram of hydrogen, since scientists are very fond in weighing things in grams. And how much is a gram? Well, take a pen cap in one hand and a nickel in the other. A pen cap weighs 1 gram. A nickel weighs 5 grams. Weigh them off and you will get a good feel of about how much a gram really is. So scientists wanted the number. They wanted to know exactly how many atoms are in 1 gram of hydrogen. Was it a billion atoms? Was it a trillion atoms? A quadrillion atoms? Was it a zillion, jillion, dillion atoms? Well, they found out the number, and yes, there are a zillion, jillion, dillion atoms in 1 pen cap's worth of hydrogen. And they gave that gigantic number a special name. They called it the mole. Yes, the mole. And it's pronounced and it's spelled just like the furry burrowing animal, mole. It is spelled just like the animal mole, except it's often abbreviated by removing the letter E, which really isn't much of an abbreviation at all. Now, if you think about it, the word mole actually means a mound of something. Like a skin mole is a little mound, and a burrowing mole makes little mounds of dirt, and a mole of atoms is a little mound of atoms. Several men over a 150-year period were primarily responsible for calculating this nearly impossible number, mole. And we will learn of it first by following the trail of these 4 men. The first man was the Italian physicist with the impressive name of Lorenzo Romano Amedeo Carlo Avogadro di Quarenga e di Cerreto. Fortunately, his friends just called him Avogadro for short. Avogadro. And yes, his name does sound an awful lot like avocado. Everybody thinks it, so I might as well just say it. Avocado, Avogadro. Avogadro was born in 1776, the same year as the American Revolution. He was a modest and religious man, husband to Felicia, and the father of 6 children. Essentially, his theory was this: find any gas on the periodic table, hydrogen, nitrogen, oxygen. If you take equal volumes of any gas, they will all contain the exact same number of molecules, regardless of what kind of gas it is. Now, this wasn't just some wild idea of Avogadro's. He actually proved it over a lifetime of work using some very complex formulations. But what exactly the number of atoms were, Avogadro never found out. Avogadro's work was all but forgotten until nearly 50 years later at the International Meeting of Chemists in Karlsruhe, Germany. The second man was another Italian, Stanislao Cannizzaro, and Cannizzaro handed out a paper on the very last day of the conference listing his perfected atomic weights built on the work of Amedeo Avogadro decades earlier. At least two of the young scientists present at that meeting were deeply impressed by that paper, and as we saw earlier, they were none other than Lothar Meyer and Dmitry Ivanovich Mendeleev. They took Cannizzaro's paper home and began developing their own periodic table of the elements. The third man on the trail of the mole was the gifted scientist Joseph Loschmidt, who was the first scientist to actually calculate the size of gas molecules and to estimate the amount of molecules in a volume of air. It was a remarkable feat given the information and tools he had to work with way back in 1865. It was Wilhelm Ostwald who actually coined the term mole for this approximate number. Mole was probably his short form for molecule, but really, nobody knows why he named it mole. The fourth and final man on the trail of the mole was the brilliant but humble French physicist Jean-Baptiste Perrin, who completed the work of these other men. Through complex math and experimentation, Perrin accurately calculated the number of atoms in 1 gram of hydrogen, and it was a huge number, bigger than any number conceived before it. He named it Avogadro's number in honor of the Italian scientist who started it all. Perrin received the Nobel Prize in Physics for this and for his other outstanding contributions to science. Perrin can be seen here in this amazing 1911 photograph alongside Ernest Rutherford, Max Planck, Marie Curie, and Albert Einstein. So, how much is a mole? How big is Avogadro's number? It is 6.02 times 10 to the 23rd power. That's a 6 with 23 zeros after it. If you had a mole of pennies to give to all 5 billion people on the planet, everyone would get over $1 trillion in pennies. And a bowl of eggs? That would fill the world's oceans 30 million times over. And 1 mole of marbles spread evenly over the earth would cover the planet in a layer of marbles 50 miles thick. Yet a mole of sugar molecules will easily fit in this bowl. This is because atoms are really, really, really small. In size, 1 atom is to an apple what the apple is to the entire planet Earth. Now, when you think of the Earth, you probably think of a picture of the planet Earth. To get an appreciation of the size of the atom, take the apple outside, maybe to a hill, and look around you. Then look at the apple compared with what you see. And what you see is only a tiny fraction of the entire planet. And an atom is to that apple what the apple is to everything you see around you and beyond. The mole gave an accurate count of the number of atoms in 1 gram of hydrogen. Earlier, we said if 1,000,000 hydrogen atoms weighs 1 pound, then 1,000,000 gold atoms would weigh 197 times that, or 197 pounds. It's still true, but now we know the real size and weight of atoms. So, likewise, if a mole of hydrogen atoms weighs 1 gram, then a mole of those heavy gold atoms will simply weigh 197 times that, or 197 grams. Scientists seldom use the actual number 6.02 times 10 to the 23rd in their common equations, but they are very fond of using the word mole as a unit of measure, and you will encounter it often. Here are 63.5 grams of copper, and since the atomic weight of copper is 63.5, this is 1 mole of copper. Here are 27 grams of aluminum, and since the atom weight of aluminum is 27, this is 1 mole of aluminum. And here is a stack of gold coins, weighing 197 grams. And since the atom weight of 1 gold atom is 197, this also is 1 mole of gold. There are 6.02 times 10 to the 23rd atoms in this stack of gold coins. By the way, here is a mole of water molecules. H2O, 2 moles of hydrogen at 1 gram each, plus 1 mole of oxygen at 16 grams per mole, is 18 grams of water molecules. A mole of iodine, a mole of bromine, whatever. Same number of atoms, different weights. Avogadro was right. Take any lump of any element, and as long as it weighs its atomic weight in grams, they will all contain the exact same number of atoms. They will all contain 1 mole. 6.02 times 10 to the 23rd power.